Okay, so last week I gave you a teaser, if you like, of what was going to come today by introducing you to the ordinal numbers. And I did that by saying ordinal numbers are counting to infinity and beyond. And I illustrated that by counting up through the ordinals and using various arithmetic operations on ordinals as a notation system for ordinals, but just to give you a feeling for what the ordinals are. And I'm going to start with the same thing again, only I'm not going to be so detailed, so I won't put so many ordinals on the board, but just to remind you what the principles are that we're using for counting through the ordinals. So as I emphasized last week, the idea is to count to infinity and beyond. We also call this counting into the transfinite, beyond finite. And so the main thing we did last week was we started counting up the natural numbers. So on. But you count to infinity, so you say, I recognize that I've got the set of natural numbers, and now I'll give myself a new ordinal beyond that as the place to continue counting. So I give myself such an infinite ordinal, the smallest infinite ordinal, omega, and I keep on counting, and so on. And today I'm going to stop there, because now I want to formalize what the structure of numbers we get is, but if we adopt this principle to counting to infinity and beyond. And we realize that essentially we're using three different things, ingredients. We start at 0, so we have 0. From any finite number, but also any ordinal number, we can add 1 to it and move to the successor ordinal. So we have a successor operation. And these two ingredients we have, these are the ingredients that generate the natural numbers. But with the ordinal numbers, we've got a third ingredient, and that is, once we have generated some set of ordinals, so for example, when we generated the set of all the natural numbers, we can then move beyond that. And there are various ways of formulating this, but a simple one is to say, well, and let's consider the set of natural numbers. Well, what we want is a supremum to that set of natural numbers. We want the smallest ordinal that's greater than or equal to all the natural numbers, all the ordinals we've gathered into our set. And we're going to have that as a general principle of counting. So we simply give ourselves this, and we also give ourselves 0, a successor, which takes an ordinal and returns the ordinal one above it, the next ordinal up. And we have a supremum operation. A supremum, or least upper bound. That maps any set of ordinals to a supremum ordinal. So supremum is another word for least upper bound. Yeah? Sorry?
The set of ordinals is empty.
Well, if the set of ordinals is empty, we have a supremum from an empty set, which is the smallest ordinal. So the supremum operation won't give us something new, it'll give us back 0. But we still have the supremum of an empty set. So what I'm going to do is essentially, well, there are various approaches one could take. So in most textbooks on set theory, one understands these operations by defining a concrete notion of ordinal as certain sets, defining what these operations are, and understanding these operations as derived properties of the concrete definition of ordinals. That's a bit like defining the real numbers as Dedekind cuts and understanding all the operations, so deriving the operations of addition and multiplication as, say, operations on Dedekind cuts. A more modern and more natural approach to the real numbers is to axiomatize the real numbers as a complete ordered field. And a more modern approach to the ordinal numbers is to axiomatize them as an ordered structure that supports these operations and basically has a principle that says these operations generate the ordinals. So that's the approach I'm going to do. I'm going to do an axiomatic account of what the ordinals are. But later on, we'll look at how they can be defined as special sets. So we'll also look at, if you like, the textbook, the standard textbook approach. And the whole approach I'm going to follow is completely analogous to what I followed for the natural numbers, when we first axiomatized the notion of a natural number structure, and we then later proved that we can construct a natural number structure within set theory as a set, once you've got the axiom of infinity, of special sets, namely the one Neumann numbers. So we're going to have an entirely analogous treatment here of ordinal. Now the ordinals are a bit more complicated than natural numbers, so the structure we're going to have is a little bit more complicated. And one thing we're going to do is we're going to build the order in as part of the structure, whereas with the natural numbers, we just have the successor operation and you can derive the orders. One can do the same thing with the ordinals. One doesn't need to build the order in, but it's more natural to define it. It's easier to understand if one presents it. At least I think it is, if one presents it the way that I'm going to present it. For the ordinals, the structure is going to be a class to begin with, just like our natural number structure was a class to begin with. It's going to be a class that has a zero element, a successor operation, and a supremum operation, and also carries an order. So I think I need my notes to remember what the. So I know various ways of writing this definition, and I want to be consistent with the notes. So for this course, so this is not something you find in the set theory literature, because people almost always just define the von Neumann ordinals, the ordinal special sets, and work with those. But it's I think, much more natural to do it in this axiomatic approach. So an ordinal structure, a natural number structure to begin with was a class n of natural numbers with some operations and satisfying some properties. So an ordinal structure is also given by a class which we'll call ord. And these are things that we call ordinals. So that's in quotes because that's what we call them. So we require that we've got a partial order between ordinals. because the order relation is going to be important here, in today's lecture I'm going to use a lot of technology, a lot of the technology of order relations. I've already referred to supremum here. You might remember the partial orders. I mean, of course, they're relations that are reflexive, transitive, and antisymmetric. That's in their non-strict variant, by their reflexive. There's also the strict variant in which the relations are irreflexive and transitive. But whenever you have a non-strict partial order, it determines a strict partial order, namely being less than or equal to but not equal. Whenever you have a strict partial order, it determines a non-strict one, either you're strictly less than or you're equal. So yeah, it doesn't really matter which one we take as basic, but it's kind of more natural here to take the less than or equal as basic, I think. So I'm going to assume you know about partial orders, but in today's lecture notes, there's a coda at the back, that's like an epilogue to the lecture notes, where definitions and terminology related to orders are basically revised in that epilogue, so you can refer to those. We have a partial order on the ordinals, and then we have a zero element as motivated on the other board, so an element which we'll call zero. We have a cross function, which is going to be the successor operation, which, just as we did with the natural number structure, we'll call S the successor. So this is called successor. And another class function, which I'll call sup. And this is going to be the supremum. And the class function, this class function is motivated here in that any set of ordinals, so that's any element, so its domain is the power class of ordinals, so in the classical subsets of ordinals. So it goes from power class of ordinals to ordinals. But this is called supremum. And it needs to satisfy three properties. So the first two say that the successor and the supremum behave as their names suggest. So the successor is indeed a successor operation. S is a successor operation. So here we're using successor as a name, but here I'm using it as mathematical terminology. And what this means is for any ordinal alpha, one typically uses Greek letters from early in the alphabet to range over ordinals, but early in the Greek alphabet. So for any ordinal alpha, we have that alpha is strictly less than the successor of alpha, and if alpha is less than or equal to any beta, then either beta is alpha or beta is or the successor of alpha is less than beta. Okay, so this is saying alpha is strictly less than the successor when there are no other ordinal numbers in between. I hope it's what it's saying.
What if beta is alpha plus 1?
Thank you. Yeah, very good. And so secondly, sup is a supremum operation. Meaning, for any set of ordinals, sup of x is the least upper bound of x. I.e., you want, but as I say, all this is revised at the coda of the lecture notes. So, i.e., I'll write it like this. So I shall use this. Oops, I shall use this notation very often on the course when we say a set of things is less than or equal to an element. I simply mean every element in the set on the left is less than or equal to the element on the right. In other words, the element on the right is an upper bound of the set on the left. And if x is less than or equal to alpha, then well, sup of x is the least upper bound, so the supremum of x is also less than or equal to alpha. Okay. So these are the first two properties. And the last one is the most interesting one. So with the natural numbers structure, the main property we needed to do was the property that said all natural numbers, we've got natural numbers contain zero and are closed under successor. But then a very important property was the property that said all the natural numbers are generated. Those operations alone suffice to generate all the natural numbers. And we formulated that using the ordinary principle of induction for natural numbers. We now want something similar for the ordinals. We want to say, the idea is we're counting through the ordinals using these operations, and the ordinals are what we can get to through that method of that method of counting that employs these two operations and starts with zero. And so we want to say that the ordinals are everything that we generate through these methods, and we're going to have an induction principle that tells us this. This is a very important induction principle in mathematics, and it's called the principle of transfinite induction. So this is the last axiom of an ordinal structure. Lastly, there's another bullet point, the principle of transfinite induction TI holds. So the principle of induction for natural numbers says if you've got any subset, or more generally, as we first formulated it before the axiom of infinity, if you have any subclass of the natural numbers that contains zero and is closed under successor, then that subclass is the whole of the natural numbers. And the principle of transfinite induction is basically going to do the same thing for the ordinals, including also the supremum operation. So if we have any subclass of the ordinals that contains zero, is closed under successor, and is closed under the supremum operation, then that subclass is all the ordinals, is the class of all ordinals. So if X is a subclass of ordinals is such that if it satisfies the properties that it contains 0, is closed under the successor, and it's closed under the supremum operation. So how can we say that? But this is X is a class. So to say it's closed under the supremum operation, that's saying that if we've got any subset Y of the class X, its supremum should also be an X. So for any set Y, which is a subset of the class X, supremum Y belongs to X. So if it's closed, if it contains 0, closed under the successor, and closed under the supremum, then X is the class of all ordinals. Okay, and that, I'm tempted, it's not an end of proof, it's a long definition, so let's use an end of definition symbol for a block. And that is the definition of an ordinal structure. Does that make sense? There are some things I might wonder about. So for example, with our partial order here, when we were counting last week and briefly today, and everything was neatly arranged in a linear order. So you might wonder, actually, should this actually really be that it's a linear order rather than a partial order? So let's address that. We could have said a linear order, but we're actually going to prove it's a linear order. So let's do that as our first example of the proof of a property about ordinal structures. So remember this bit, we'll keep transfinite induction on the board. So its proposition is a linear order on class of orders. Okay, so let's prove that. So, how do you think we're going to prove this? With transfinite induction. So basically, this is our one tool at the moment for proving properties about ordinals. We're going to prove this by transfinite induction. Of course, this is a binary relation, so we'll have to do an induction. We'll have to choose which side of the relation to do an induction on. So we'll do it from the left-hand side. So let beta be an arbitrary ordinal. We're going to prove by transfinite induction on alpha that the linearity property holds with respect to alpha and beta, so namely either alpha is less than equal to beta or beta is less than equal to alpha. So we can show we'll prove that this junction alpha is less than or equal to beta, or beta less than or equal to alpha holds, so this disjunction holds for all alpha by transfinite induction, and we say it's transfinite induction on alpha, because that's the variable we're doing transfinite induction. So by transfinite induction. So what this means formally is we consider the class of all that we fix beta, and we consider the class of all ordinals alpha that satisfy this property. I mean, we're going to show that it's closed under these three conditions. So we need to. So it's like ordinary induction. We have a base case. Maybe I should write this. So this is the base case. We have a step case or a successor case. And we have a new case to prove, which is the supremum case. So let's just treat these one at a time. So base case. Well, the base case is alpha equals 0. And in that case, obviously, I forgot an axiom about the ordinal structures. So there's a mistake in the definition of ordinal structure. The further property is that 0 is less than or equal to every ordinal. So yes, that should have been part of the definition. That's in the notes. It must be. But even though I was reading from the notes, I thought I managed to skip over that. Yeah. Yes, indeed. So I have 3 bullet points on the board. There are 4 bullet points. And the first of those 4 bullet points is that 0 is less than or equal to beta. So sorry about that. Anyway, the base case, 0 less than beta holds by the missing axiom. So that helps the description holds trivially. The step case. So as always with the step case, we have an induction hypothesis, which is that alpha belongs to X, and then what we want to show is that the successor of alpha belongs to X. So the induction hypothesis is that either alpha is less than or equal to beta, or beta is less than or equal to alpha, and we want to prove that the same instruction holds for the successor of alpha. That either the successor of alpha is less than or equal to beta, or the successor of alpha, or beta is less than or equal to the successor of alpha. So to prove this, well, suppose the successor of alpha is not less than or equal to beta, and then we'll hang on. Is that what we're going to do? No, we're going to, of course, use the induction hypothesis, which gives us 2 cases. So we'll either use, by the induction hypothesis, we either have the case that alpha is less than or equal to beta, or beta is less than or equal to alpha. So in the case that alpha is less than or equal to beta, we have well, if alpha is less than or equal to beta, then by the successor axiom, either either alpha equals beta, or the successor of alpha is less than or equal to beta. So that's the successor axiom. The successor axiom. And if alpha equals beta, then beta is less than or equal to the successor of alpha. So beta is less than or equal to the successor of alpha, or successor of alpha is less than or equal to beta, which is what we want to show. It's not fair, okay? And in the case that beta is less than or equal to alpha, then, well, clearly, because alpha is less than the successor of alpha, clearly beta is less than or equal to the successor of alpha. Then beta is less than or equal to the successor of alpha. So we've got those two cases, and by the induction hypothesis, these two cases cover everything. Okay. So finally, we have the supremum case, which we're not used to dealing with in inductive proofs. It's not part of our familiar proof by proofs by induction meet everyday mathematics. So the supremum case, and I want to stick close to my notes. So for the supremum case, let's suppose that A is a set of ordinals alpha satisfying that alpha is less than or equal to beta, or beta less than or equal to alpha. And what we need to prove is we need to prove that the supremum of the set A also is either less than or equal to beta, or beta is less than or equal to that supremum. We need to prove the disjunction that supremum of A is less than or equal to beta, or beta is less than or equal to the supremum of A. Okay. Now, because this is the supremum, it's the least upper bound, this left one holds if and only if every element of alpha is less than or equal to beta. So we consider two cases. Or there are two cases. There are two possible cases. So in the first case, for all alpha in A, alpha is less than or equal to beta. We know for all alpha in A, this disjunction holds, but maybe for all from the left hand, one of the disjunction holds. So in this case, since the supremum is the least upper bound, the supremum of A is less than or equal to beta. And the other case, well, if it's not the case that for all alpha in A, alpha is less than or equal to beta, then, well, there must be some alpha in A such that the other disjunct holds. So there exists some alpha in A such that beta is less than or equal to alpha. For the second case, because we know this, the disjunct holds for all alpha in A, so either the left-hand side holds for all of them, or there is at least one for which the right-hand side holds. So if there's one for which the right-hand side holds, we have an alpha in A such that beta is less than or equal to alpha, and in this case, well, beta is less than or equal to alpha, but alpha is in A, supremum is upper bound, so that's certainly less than the supremum of alpha, so beta is less than the supreme of alpha. Okay, so we covered the three cases. Sorry, successor. Supreme of A. No, hang on. Yeah, supreme of A. So three cases together. So by transfinite induction, we have proved all alpha is listening to beta or beta is listening to alpha. Okay, so now the end of definition box is now conveniently placed as an end of proof box, which is useful. Okay, so good. There's maybe a point to raise about this step. Does anybody who's sensitive to logic?
Yeah. So I think that's sorry, I didn't cut you off. I think I want to ask that. So how do we get from the negation of alpha that's equal to beta that's equal to alpha, and we use the induction hypothesis?
Yeah, so the induction hypothesis is that this disjunction holds for all others today. So that's why we get one of these two cases.
Yes, that's what I want to ask.
Okay. Yeah. But there's another logic point.
Okay. So it's logical. We use the logic.
So it's also, for those of you who are sensitive to issues about classical logic versus constructive logic, this very much uses the law of excluded middle. And one of the reasons for giving the axioms to the ordinal structures in the way I gave them is that also, the axioms I gave also make sense intuitionistically. And intuitionistically, the ordinals satisfy a good intuitionistic notion of ordinal satisfies those axioms, but it's not the case that they're linearly ordered. So here's the place. So one can establish using classical logic, and we're working with classical logic in this course, that the ordinals are linearly ordered. Right. Good. Well, we've got the definition of the ordinal structure. We've had one proof by transfinite induction, and I think that's a good point to have a break. Are there any questions? No? Okay. Okay, so when we looked at the natural numbers, every natural number had an important set associated with it. We had the standard finite set. Standard finite set. Let's put the article in. We call the standard finite set for a natural number was defined to be the set of all natural numbers strictly less than n. And it always has the same cardinality of the natural number, and we use such sets to define finite cardinalities. They're not going to be so associated cardinalities here, but a similar definition makes sense for an ordinal. So we're going to define the standard ordinal set. We use the same notation, square brackets alpha. So at the moment, we're going to define it as a class because the ordinals, we've axiomatized them as a class. When we have the natural numbers, we have the axiom of infinity in the end that says the natural numbers are a set. And at the moment, the ordinals are a class. So this is the class of all ordinals. Beta. Such that beta is strictly less than alpha. And just to say, I decided to use this notation 5 minutes ago. So in my handwritten notes, so in the notes, I use the notation down arrow alpha. Okay, but it seems sensible to use this to unify it with the notation you have. The natural numbers. Okay, so this is for every ordinal determines the set of ordinals, well, the class of ordinals strictly below it. But I keep on saying set, and there's a reason for that, and that's because it's going to be a theorem or a proposition. Proposition in there, so let's keep it the same. So for every ordinal alpha, the class ordinal strictly less than alpha is a set. And that's quite intuitive. If you think that we're counting through the ordinals, we're generating them from below, and you know, somehow, although we're doing infinitary stuff, we stay within the. We only have to do a set of work to generate a set worth amount of work to generate any ordinal, whereas somehow the whole like class of what's to follow sort of lies in front of us, or something like that. Anyway, it's a mathematical statement. This class is always a set, and we can see that by proving it. And how are we going to prove it? Sorry?
Induction.
Transfinite induction, because it's our only way of proving, at the moment, of proving that the property holds every ordinal. So, by transfinite induction, on alpha this time, so the base case, alpha is 0. So Y is the class. Y is the class of ordinals strictly less than 0 set?
Because
it's the empty set, which is a set. That case, the induction hypothesis, IH, the induction hypothesis, is that the ordinals strictly less than alpha is a set. The class of ordinals strictly less than alpha is a set. Then what is the class of ordinals strictly less than the successor of alpha?
the ordinals in alpha plus alpha.
So something's by the successor axiom that says the successor is the smallest thing strictly above alpha. If something's strictly below the successor of alpha, it's either alpha or it's strictly below alpha itself. So in other words, it's either something strictly below alpha or it's alpha. And this is the set, and we're dealing with the singleton, so clearly a set. Clearly a set. And the supreme case, suppose that alpha is a set. This is the induction hypothesis. For every alpha, it's some set. Well, let's call it again A, where A is a set of ordinals. In this case, the set of ordinals strictly below the supremum of A, you can work it out. It's simply the union over all alpha in A of the sets of ordinals strictly below every alpha. And A is a set, and it's a set index union of sets, so again, the set. a set
because
sets are
sets
closed
are closed
under index UD.
Excuse me, just one second.
Index by sets. Let's write that in a nice way under unions indexed by sets. Yes, correct.
Okay. So to form such unions, we need the axiom of replacement problem. Right.
Yeah, so whoops. So I wish I'd actually done this in the first lecture in this way, but the axiom that a set index union of sets is a set is equivalent to the axioms of the conjunction of the axioms of the union and the replacement axioms. Okay. So it's a straightforward exercise to prove it. Yeah, it doesn't indeed require the replacement axiom.
I have a further question.
Yes.
So my speculation is that we can probably even prove that the standard ordinal class of alpha is equal to alpha.
No.
No. Okay.
Just like we can't prove the standard natural number n is equal to n. We can prove the von Neumann, that's true for von Neumann numbers.
Yeah.
So you want to prove how?
Yes.
You want to prove that?
Yes.
But we haven't said anything about what the elements of the ordinals are. They don't need to be. So this will hold for von Neumann ordinals. So we define von Neumann ordinals. But the point is that it's irrelevant what objects of our universe our ordinals are. Or what matters is your graphic structure. It's just like it's irrelevant if your real numbers are Dedekind cuts, or if they're equivalent classes of Cauchy sequences of rationals, or some other chosen representation, or if you like, infinite sequences of decimals that define real numbers. I mean, there are many ways to define the real numbers. None of them matter because you always have a complete ordered field. Same way for the ordinal structures, there are many different set theoretic ways one can define an ordinal structure. If one defines this as the von Neumann ordinals, one will have this. But if one defines it in a different way, one won't. And this is the kind of question this is the kind of statement one shouldn't include in mathematics, because here you've got an entity, a number, and here you're equating it to a set. And I think the modern way of thinking, one just shouldn't make statements like this. This is a set of ordinals, and this is a single ordinal. And you can code things up so that this holds, but nobody in real life says the number 5 is the set 0, 1, 2, 3, 4. There's no number here is good. As I say, that's what the number 5 is. Well, maybe some strange one would. Anyway, there we go. So for every ordinal, you've got a set of ordinals strictly below it. But what about looking into the future? So as we're looking at above, so a question is that there's a clear analogy with how we dealt with the natural numbers structure. With the natural numbers structure, in the end, we wanted our natural numbers to be a set, because then we can deal with it like a set. So we might say, well, can we have a super axiom of infinity? Or maybe we can already prove the ordinals form the set. Or maybe we can have a super axiom of infinity that says the ordinals are a set. Only you can't, because actually what we're now going to prove is that the ordinals are a proper class. Necessarily. There's no way, you cannot assume that the ordinals form a set. So this is where the ordinals really differ in a big way from the natural numbers. and so let me put it down as proposition. Ord is proper class. And this is very easy. So suppose not. So if it's not a proper class, then I suppose Ord is a set. But if it's a set, then we can apply the supremum operation to it, because the supremum operation is applicable to any subset. So sup of Ord is then the supremum of all the ordinals. In other words, it's a maximum element in the set of ordinals. Is a maximum element in the set of ordinals. But why is this a contradiction?
Because you can always get bigger.
How?
With distances.
Yeah. So then, yeah, if this is the maximum element, well, where does the successor? Yeah, what happens to the successor? That's a strictly larger element, and but this cannot be so. This cannot be, because the successor of sup or Ord is strictly larger. So I've got a contradiction, and there we go. Okay, so the ordinal structure, we've satisfied some properties. You know, we've axiomatized what the structure of the ordinals is, but it has this characteristic that it's necessarily and provably a class. And I think this is the fact that causes the ordinals to be dealt with in sort of maybe not very mathematically lovely ways when used in mathematics. Mathematicians often tend to avoid using the ordinals. Not that many mathematicians know that much about the ordinals. And I think one of the reasons is that in set theory books, the ordinals are basically often presented just as what we're going to call later in the lecture the von Neumann ordinals. They're presented via an encoding, and that's something that's unpalatable to deal with. And they're presented in that way because if one wants to deal with them axiomatically, as we're doing, one has to take classes seriously, because the structure is a class. But in modern mathematics, one's quite used to taking classes seriously. So for an area such as category theory, for example, one often deals with structures that are essentially classes. The collection of objects of many categories that one deals with on an everyday basis is a class. So nowadays, mathematicians are used to dealing with classes as the carriers of mathematical structure. And if one is happy to deal with classes as the carriers of mathematical structure, there's no problem to have a nice axiomatic approach to the ordinals, which is that I'm presenting in this lecture one way of doing that. But somehow, mathematical practice concerning the ordinals has not really caught up with modern mathematical standards, as far as I can see. Most people and certainly in set theoretic textbooks, the ordinals are almost universally, I would say, universally introduced as higher encodings as the von Neumann ordinals, which we'll consider later. Okay, so the ordinals are a proper class, but for every ordinal, the ordinals strictly below it form a set, linearly ordered, so we're now going to go and proceed to do some well, we want to set up the machinery to allow us to start doing arithmetic with the ordinals. And this arithmetic was something that I was using last week when I counted through the ordinals, and I was writing ordinals using notations, including using addition and multiplication and exponentiation as part of the notation. So what I want to work towards is now introducing these operations on ordinals, the arithmetic operations on ordinals. But before doing that, let's look a little bit more closely at the structure of ordinals to understand them a bit better. So basically, well, we can split the ordinals into two kinds of objects. And ordinals are either let's put it like this, every ordinal, alpha, is either a successor ordinal so that means it is the successor of some other ordinal. So there exists some beta such that alpha is the successor of beta. Or, and such a beta is unique, proof, or it's a limit ordinal. How do we define limit ordinal?
Negating.
Oh, well, one could do that. But we want to define it in an interesting way. So being a limit ordinal means we get it via a supremum operation, but every ordinal is the supremum of the singleton set containing just that ordinal, so we don't want to get it in the trivial way as a supremum operation. So what we mean is it's a supremum of ordinals strictly below it. So we could write it as this. There exists a subset of the ordinals strictly below alpha, such that alpha is the supremum of A. Or equivalently, so this 3 lines of Ly after means equivalently, we can simply say alpha is the supremum of the ordinals as a set of ordinals strictly below. Okay. And this last one's a more useful characterization. And these are mutually exclusive. So it's really either or in the traditional linguistic sense. So let's emphasize but not both. And here I'm making, again, a statement about every ordinal. So once again, it's a statement that one should prove. I'm not going to prove it, it's an exercise, but prove it by transfinite induction. And this classification is a little bit useful because it's often helpful to reformulate structural and not structural. Again, transfinite induction in a way that makes use of this distinction between ordinals. So I'm going to actually present to you with a reformulation, a useful reformulation of transfinite induction. A reformulation of transfinite induction. So again, we call it transfinite induction, but this particular one is the zero successor supremum, or sorry, rather limit, because we're going to measure a limit ordinal limit formulation. That's the zero successor limit version of transfinite induction. So it's basically going to be similar to what we had before. If we have a class of ordinals, and if it satisfies that, again, it contains zero, it's closed under successor, but in the third case, we simply ask for it to be closed under the supremum operation, so we can restrict to supremums of the sets of ordinals strictly, but to suprema, rather, that's the right order of supremum, the suprema of the sets of ordinals strictly below the given ordinal, when the ordinal is a limit ordinal. Because here we're dealing with successor ordinals, our third case only needs to cover limit ordinals, and so it's enough to say that lambda belongs to the set to the class X whenever all the ordinals strictly below it belong to X. Okay? So this is the limit where lambda, so I should have said every ordinal is one of these two. So in particular, 0 is a limit ordinal because it's not a successor, and it's the limit ordinal because 0 is the supremum of the empty set, which is 0 in square brackets. But here we've already said 0 belongs to X, so we don't need a case. Let's try. The point here is we're making the cases mutually exclusive. So here we ask lambda to be a limit ordinal. And what's nice about this version of the statement of transfinite induction is there's no redundancy between these three conditions. There's no overlap between them. Each ordinal is dealt with by exactly one at the right-hand side. So then, of course, X is the class of all ordinals. Okay?
It seems to me that lambda can be the zeros to the empty set, so they are not.
So sorry, yeah. I meant to write that as well. And lambda greater than 0 is the limit ordinal. Yeah, sorry. About if it was supposed to be no overlap. And just to say, there's another version that one often sees in transfinite induction. That one often sees for transfinite induction, which I'm going to call the uniform version. And that says if X is a subset of ordinals, sorry, subclass of ordinals, that satisfies. Now the point here is, suppose we dropped the greater than 0 condition and just asked for a limit ordinal. Well, in the case of 0, this would say the empty class is a subset of X, the empty set is a subset of X, which always holds. So this condition would actually be saying the same thing as this if we applied it to lambda equals 0. And also, if we say exactly the same condition for a successor ordinal, then it literally says this. Well, it says It doesn't actually literally say this, it says something stronger. It says if all ordinals less than or equal to alpha belong to X, then the successor of alpha belongs to X. But it gives us a slightly stronger induction hypothesis. The point is, it's still a valid induction principle because we have an even stronger induction hypothesis. So the point is, one can use just this condition to get a valid form of transfinite induction. And this is the form in which it's very often used. So the uniform version is a very neat version, which is whenever X holds for all ordinals strictly less than alpha, X holds for alpha. If that holds for all ordinals, then X is the whole class of ordinals. Okay. So this is rather nice because everything's dealt with nicely and uniformly by this one implication there. Okay, are there any questions about that? Okay, so now I want to move on to what I've already mentioned before, which is defining the arithmetic operations on ordinals. And you may remember we did this for the natural numbers. I think in the lecture I maybe covered the definition of addition. And we did it using a theorem, which was a theorem that holds for any natural number structure called the recursion theorem. And we're going to have an analogous theorem for the ordinals. And the analogy is very strong in that for the natural numbers, you have the property of induction that allows you to prove that every natural number satisfies a property. And then you have the principle of recursion that allows you to define functions whose domain is the set of natural numbers kind of inductively. It's like an inductive definition of a function by defining it on zero and saying what you're going to iterate to define what function you're going to iterate to define the function on the higher numbers. That was the recursion theorem for natural numbers. Yeah.
So, could you just really quickly walk me again through how from this uniform version we derive the case for the successor, because it's not bad.
So suppose this holds. That if suppose which way are we trying to do it?
So from the uniform version, derive the case from the successor, the zero successor increment. So we presuppose the uniform version and we derive that for alpha in class X is going to follow the successor of alpha.
So what holds the two induction principles are the same, namely the induction principle that says under this condition holding for all ordinals alpha, this holds, and the condition that says under these three conditions holding for all ordinals alpha, this holds. It's not the case that this condition for a single successor ordinal alpha implies this condition for a single successor ordinal alpha. But the whole induction principle here is equivalent to the whole induction principle here. And it's the same idea as the equivalence between, for natural numbers, what people sometimes call induction and complete induction. Where complete induction is where you assume the induction hypothesis for all numbers strictly less than that. Or strongly, yeah, I mean, there are various ways, but of course, the values induction, people sometimes call it in English as well. This is basically the same idea. Yeah, so good question. So let me state what the transfinite. So we're going to have an analog recursion theorem that allows us to define functions on ordinal numbers. So this is
called the transfinite recursion theorem.
And this,
for me,
is a statement of this theorem in this abstract form using ordinal structures and using classes and class functions. It's so much cleaner than if you look in set theoretic books, how this theorem's formulated in terms of von Neumann ordinals. It's very, I find it very hard to read the standard set theoretic formulation. So I think the formulation of this theorem is a big win for me. A more abstract approach to that following the lecture. So it's called the transfinite recursion theorem. So just as we went from induction for natural numbers to transfinite induction for the ordinals, like counting you to the transfinite, so beyond the finite, we go from the recursion theorem for natural numbers to the transfinite recursion theorem. If you like, the TRT. And it's again going to say what data we need to specify on a set or a class, which is going to be the codomain of a function, in order to generate a function from the ordinals as domain to that class as codomain. So in that aspect, it's exactly analogous to the recursion theorem. So let A be a class. And which is going to be the codomain. And like in the recursion theorem, we're going to give a starting element, which is where we're going to map 0 to. We're going to give a function from A to A, which we're going to use as the operation we apply to successor rule. When we have a successor case, so to go from the case for the previous ordinal to the case for its successor. So this is the function we're going to iterate, but we need a third piece of data to deal with the limit ordinals. So for that, we ask for a function L, which is a function that maps every subset of A, so from the power class of A to A. So given that data, there is a unique class function from the ordinals to the domain to the codomain class A, satisfying does the expected thing. So we map T of 0. The whole point of having the element little a is something to map 0 to. T of the successor of an ordinal is, well, the point of F is to tell us how to get where to map the successor from. We apply F to what we get from applying T to the predecessor. And then on the limit ordinal, so having this classification into 0 successor and limit ordinals greater than 0 allows us to have 3 mutually disjoint cases here. So for a limit ordinal lambda, that's where we apply the L operation. And of course, the canonical set we use here is, so we apply L to a set of elements of things from A. And the set of elements is, well, we'll apply it to F of alpha, the set of all F of alpha for all alpha in strictly below lambda. Okay. Where again, lambda is greater than 0 is a limit ordinal. don't need to say is have lambda greater than 0 and limit ordinal. Okay, so that's the theorem. Now, we have an analogous theorem for the natural numbers, which I didn't prove in the lecture about natural numbers structures. Here we've got another theorem, but it's a bit more complicated. And because I haven't proved the recursion theorem, I do want to give you an idea in this lecture about how the proof of the recursion theorem goes. But it is a bit technical, so I'm going to leave that for the end of the lecture, and I'm going to go, before that, I'm going to look at applications of this theorem. Okay, so a first application from this recursion theorem is a corollary. If we have two different ordinal structures, then they're isomorphic. Meaning there's a bijective class function from one structure to the other, whose inverse obviously gives a bijective class function in the other direction, that preserves the zero, the successor, and the supremum operations. Yeah, and that's all you need. That's an isomorphism between ordinal structures. And I'm not going to give you the proof of the corollary, but it's basically straightforward. If we've got the ordinal structure we started with, or suppose we've got another ordinal structure, well, let's say A is its class of elements, then we simply take 0, the 0 ordinal in A as our little A, the successor operation on A as our F, and the supremum operation on A as our L. And then we get a unique class function defined like this. Because that's an ordinal structure, we can apply the same transfinite recursion theorem to that ordinal structure to give us a function back. And then the composites of those two functions in either direction are going to be the identities, because they will preserve 0, preserve successor, and preserve the limit, and then the unique by this theorem, there's a unique such class function, and since the identity is such a function, then the composite must be the identity. That's basically the idea of how one proves.
Excuse me, just one detail. So if F is the successor, then we're gonna have so we're gonna be leaving out 0 basically, because we're gonna be leaving the whole
No, because so we have our initial ordinal structure, or we're assuming we've got some other ordinal structure, which I'm calling A here.
Yeah.
We take 0 in that ordinal structure for little a. So we get 0 preserved in this direction.
Yes.
We do the opposite thing to get a function back in the other direction. We apply the transfinite recursion theorem. So we're going to derive this from the axioms for an ordinal structure. So the transfinite recursion theorem will also apply to A. It can also be, we can apply the transfinite recursion theorem applied to instantiated for the ordinal structure A to give a function back, using this as the codomain in this case, and use 0 in that case, and then both functions will. I suggest we take this in the break if you're Okay, so that's the transfinite recursion theorem. In practice, it's useful to have what's called a parameterised version of it, which we already had such a distinction for the natural numbers. So let me just modify the theorem to say how we parameterize it. And the idea is we simply give ourselves a class, another potential argument, maybe classes. And we give Z as another argument everywhere. So we'll have, see how it's formulated here. So instead of A, I have B. So we make this a function from the parameters to A. F is now given parametrically in Z. So we add Z as an argument here. We had something similar for the natural numbers. We add Z as an argument here. And basically, we simply put in Z as an extra argument everywhere that we apply T. Here we have B of Z, Ft Z alpha, and this also needs to depend on Z. Maybe it's best to just write this all out again. So the point is we now have an initial value depending on Z. So we give ourselves Z as an argument and we get the initial value as given by Fz. In the case of successor, well, we take F, we use the parameter to see which version of F we're using. So it's F in that parameter, and we're going to apply that to T. Again, we keep the parameter the same, T applied to alpha. So we simply add the parameters everywhere. And again, T of Z lambda is now L, again, using parameter Z, of the set of all of F of Z alpha for all alpha in the set of ordinals strictly below lambda. And that is the transfinite, that is the parameterized transfinite recursion theorem. So the parameters, there's a little bit of clutter. The proof of the version with parameters is essentially the same as the proof of the version without parameters. There's just more notation involved because you have to write the parameters everywhere. When we come to do the proof at the end of the lecture, I want to not deal with that notation, so I'm going to prove the unparameterized version. But the parameterized version is the one we're going to apply immediately at the start of the next hour in order to see some applications of this theorem. Okay, but it's now 4 o'clock, so we're going to have a break. Did I forget to close the parenthesis? Well, there we are. So let's close the parenthesis, put a full stop on this hour, and we'll start again in 15 minutes. Okay. So as Gregor pointed out in the break, there was quite a bad mistake in my statement, both the recursion theorem and the parameterized recursion theorem, in that this doesn't type check here. F can't be applied to alpha is an element of class of ordinals, and F second argument is something from A, and this should be T. And the whole point of this was to take the limit operation applied to collecting together the result of applying the function being recursively defined function, the function being recursively defined to ordinals strictly smaller than lambda. Okay, so now it type checks and it's correct, and the corollary now more obviously follows from the theorem. So what I want to do is apply the theorem to define ordinal addition. Just as our first application of the parameterized recursion theorem for natural numbers was to define addition on natural numbers. So we will use the parameterized TRT, transfinite recursion theorem, to define addition so we're going to define this as the unique T given by the theorem determined by some suitable data. So we need to give a base function. So the base is what we're going to do if we apply t to beta. Let's call that. So this is our z. So our z class is the class of ordinals, and our A class is also the class of ordinals here. So everything's the class of ordinals, and we want this to be addition. So so the idea is any ordinal plus 0 is going to be that ordinal beta. So the B of beta is going to be beta. We want F to be the successor operation that takes us from, if we're given, so we think of so T of Z alpha is going to, so T of beta alpha is going to be, we think of it as beta plus alpha. And if we want the successor of, if we want to add alpha plus 1 to beta, we want to get the successor of that. So T of beta alpha is going to be, we're defining these functions here, so it's going to be the successor of alpha. And L of beta of
Maybe F.
A.
F instead of B.
Sorry, F. Thank you. I seem to have a confusion in my head between T's and F's, but some pure reason. Maybe next time I give this lecture, I'll try changing T to some other letter and see if that helps. Anyway, L beta of A is simply going to be so L takes an ordinal, a set of ordinals, and we're simply going to return the supremum of A. Okay, and we're going to see what this gives us. So let's have a look at, let's maybe keep that like that, and I'll use the right-hand side of the board, see what it gives us. So let's have a look at what happens if we apply F to beta and 0. So not F, T. We want to see what function I've told you it's going to be addition, but let's understand addition by seeing what function T we get from this initial data. So we look to see what happens if we apply T to beta of 0, and T beta of 0 is B of beta equals B of beta, which equals beta. So if we add, we think of T as addition, and we're saying if we add beta to 0, we get beta back. So that's intuitively correct. T of beta and the successor of alpha. The successor of alpha is F of beta of T of beta together with alpha.
T beta together with alpha, which is, by definition of F, the successor of T beta of alpha. So if we add beta to the successor of alpha, we get the successor of beta plus alpha. So this coincides with what we expect from addition on the natural numbers, and we're just generalizing those principles to ordinals. So this is applicable to arbitrary ordinals, beta alpha. And here we're only saying what happens to successor ordinals. But finally, what happens if we apply beta to a limit ordinal lambda? If we apply t to beta together with a limit ordinal lambda, well then we get L of beta of the set of all t beta alpha for alpha strictly below lambda, which is supremum. So L is the supremum of the elements in this set. So it's the supremum of T beta alpha and how we would normally write these equations, well, so here I've been very I've said exactly what initial data we're giving, and then I'm defining a t and I'm writing out the equations that t satisfies. But in practice, the way we would normally write this, we would say something more briefly. We would say we would normally say we would use the notation we want to use. The plus on ordinals by transfinite recursion. We don't normally bother to say it's parameterized. And we simply would give these three equations using normal notation. So we would say beta plus 0 is beta. Beta plus the successor of alpha is the successor of alpha plus beta. And beta plus lambda is the supremum of this, which we would often write like this as the supremum over all lambdas strictly less than lambda, of all alphas strictly less than lambda of beta plus alpha. And probably write brackets like that. Okay. So this is how one painfully gets it from the theorem, and this is, once one's got accustomed to it, what one writes instead. Okay. And notice that if we define beta, so if we define notation, we define 1 to be the successor of 0, then alpha plus 1 by this definition is the successor of alpha plus 0, which is the successor of 0. Which is the successor of alpha. So alpha plus 1 is the successor of alpha. Okay. So this answers Yore's question on Zoom from the first hour, how the structure relates to the arithmetic operations I was using last week. You can also prove from these definitions here that NB, so we define omega to be the supremum over the natural numbers. There's an inclusion from the natural numbers to ordinals, which is obvious, so I'll just say the supremum of this. And we have from this, we can see that 1 plus omega, from this definition, 1 plus omega equals omega, which is not equal to, of course, the successor of omega, which is omega plus 1. So we can see that we get the failure of commutativity condition. And 1 plus omega is equals omega because 1 plus omega is defined as we've got a limit ordinal on the right-hand side, and we're defining it as the supremum of 1 plus n for all smaller, for all n that is for all ordinals alpha that are strictly smaller than omega. Those ordinals are exactly the finite ordinals, and so the supreme. So we've got the supremum of 1 plus n finite numbers n, and that's the supremum of finite numbers. So that is just omega. Okay, that's why we get that. And now we've got this more streamlined approach to defining the functions. Let's now define multiplication and exponentiation. So multiplication and exponentiation, if I write like this, meaning two-place operation that I'm going to use the usual exponential notation for. So these are also binary operations on ordinals. Are the unique functions defined by the parameterised transfinite recursion theorem satisfying. And I'm going to put beta and alpha in the opposite order just to be alphabetical about it now. So satisfying, well, again, we're going to define them recursively on the right-hand argument with the usual recursion for the zero and successor case, but we have another case for a limit ordinal, and for a limit ordinal, we always just do this supreme. So it's the canonical way of dealing with limit ordinals. So for multiplication, alpha times 0 is, of course, 0. Alpha times the successor of beta is, of course, alpha times beta plus. Well, I say, of course, you have to think for a bit what's going to give us the nicest operation here, because plus is not commutative. We'd actually get something different if we wrote it the other way around. So this is the version that gives us a nice multiplication operation. And alpha times lambda, a limit ordinal, is so I should have said here, again, lambda greater than 0, a limit ordinal. That's in the transfinite recursion theorem, and I won't bother to say lambda greater than, I won't bother to write lambda is greater than 0 in a limit ordinal here, but I'm assuming it. So again, this is the supremum, however, all ordinals beta below lambda of alpha times beta. And exponentiation, well, defined in the same way on, then we did the recursion on the exponent. So alpha to the power of 0 is, of course, 1, even in the case that alpha is 0. Alpha to the power of successor of beta is alpha to the power of beta times alpha. So we multiply on the right. So again, again, actually multiplication is non-commutative, but I'll come to that in a moment. Let's finish exponentiation. And alpha to the power of the limit ordinal lambda is once again the supremum over strictly smaller ordinals of alpha to the power of beta. So those are the arithmetic operations. And in this case, it's nice to work out some simple examples to see how commutativity fails, and to see other things. So in this case, we have that 2 times omega is equal to omega, which is not equal to omega plus omega, which is equal to omega times 2. Okay, so that's the failure of commutativity for multiplication. So So for exponentiation, it's not really interesting that commutativity fails because it fails also for the natural numbers. So we expect commutativity to fail for exponentiation. But what maybe is interesting is this, that if you look at omega squared, then this is omega times omega, and that's not equal to omega. Whereas if you look at 2 to the omega, this is, this is equal to omega, which is not equal to omega to the omega. And this is this what I wanted to say. Yeah. And these kind of contrast with equalities we have to do with cardinalities, whereas so for cardinalities, if we look at aleph 0 squared, then this is the same as aleph 0. So we don't have, so here we have a non-equality between them, here we have an equality. And if we look at 2 to the aleph 0, then of course that's strictly greater than aleph 0. But this equals aleph 0 to the aleph 0. So basically we have, yeah, I should have put this. Should have put this like this to make it a bit clearer. But basically, the equalities that hold for ordinals are very different from the ones that hold for cardinals. It might be more natural thinking about cardinals, but there's a whole new world of a different kind of arithmetic, non-commutative arithmetic for ordinals. Okay, so those are the arithmetic operations. So there are two other things to do. But let's not dwell on them too much. So one is to say, so we've got this abstract account of what the ordinals are, axiomatized as the ordinal structure. So how do we know they make sense? And we can do that like we did with the natural numbers, which is as a theorem, we can simply prove, which is an ordinal structure. We can prove from the axioms of set theory that an ordinal structure exists. And we define for this we define a specific ordinal structure, the class of von Neumann ordinals. Where we basically continue the idea of von Neumann numbers, where we start with, we encode 0 as the empty set, we encode 1 as the singleton empty set, 2, so we did this in 2 as this set, and we always get to the successor, is encoded as previous number set union the singleton containing the successor. So those are the von Neumann natural numbers that we looked at in lecture two, in the first lecture. But once we have the von Neumann natural numbers, we can collect them all together and get omega. So this is simply well, let's write it like this. So 0, 1, 2, 3. It's all the von Neumann natural numbers. And then we've got a successor operation omega plus 1, which is, again, omega union. We simply add omega as a new element. We take all the elements before and add omega. And we can keep on going like that. And essentially, what we're doing is we're defining an ordinal structure generated by 0 is defined to be the empty set. The successor of an ordinal is defined to be the ordinal set together with its singleton, just as we defined the successor of the natural number. And the supremum of a set A of ordinals is just defined to be the union of the set A. So just collect all the elements of all the sets in A. And these three operations taken together, we take the smallest class of sets that contain 0 and are closed under these operations. We get the von Neumann, the class of von Neumann ordinals, and we can prove that this is an ordinal structure. So we can prove that the smallest class of sets closed under the above operations is an ordinal structure. Less than equals is simply subset. Okay. So, from once, one can simply say these are the ordinals, and you can, when you work with ordinals, you just work with their von Neumann encodings. And in mathematics, people actually do that. As I say, it's kind of that habit of people is not really very modern in style. And I think it's much better to have the axiomatic account of the class of ordinals with the properties it satisfies in transfinite induction as a way of understanding the order. Okay. So the remaining thing to do is to prove the transfinite recursion theorem, which I don't have on the board anymore. And I don't want to spend very long on it because it's quite technical. So I want to give you a flavor of how one proves these kind of things. And then we'll see how long, I just probably won't take up all the time with it. So let's try and do it in 2 blackboards. We'll remember the transfinite recursion theorem. And we will start the proof, and we'll, as we go along, remember what we need. And we're given, let's just say we have the codomain class A. We're doing the simple version, so we just start with an element of a function that we iterate to get the successor case, and and another function, the limit case, that takes any subset of A at A. And we need to prove that there exists required to prove, R2P, required to prove that there exists a unique T from ordinals to A, such that this time I'll get it right. So we didn't actually have the unparameterized one correctly stated. So T of 0 is A, T of the successor of alpha is F like T of alpha, and T of a limit ordinal lambda strictly greater than 0 is L applied to the set of all F of T of alpha for alpha in this strict down set of lambda.
What if you have F?
Because that's amazing, isn't it? I don't know. I feel like I think it needs to be a brain discussion. That's a very good question. So how are we going to find such a T? And I mean, what I really want to get across is the following approach, which is the same approach that's used to prove the recursion theorem for the natural numbers. And it's a powerful idea, which is we can't simply define such a T at one fell swoop. So what we'll do is we'll define what it means for a function to approximate T from below. And we'll prove that for every ordinal alpha, there is an approximation to T defined on the ordinals below alpha. And then we have such approximations for the ordinals below every alpha, and we simply it'll be a fact that they all agree with each other, and so then we can just, and we want to find T of an alpha, we take the approximating T for alpha plus 1 and use that to get the result of T of alpha. So actually I'm going to use gamma for the approximations. So for an ordinal gamma, what we're going to define what we mean by a gamma approximation to T. A gamma approximation to T, but I won't bother writing to T because we're only going to consider approximations to T, is a function defined on the ordinals strictly below gamma. So now it's a set function because this domain is a set into the class A that satisfies these properties, only these properties restricted to the domain of little t, so the down set, the ordinal strictly below gamma. So t, little t of 0 is equal to A if 0 is less than gamma. T of successor of alpha is f of t of alpha if the successor of alpha is less than gamma. And t of lambda, a limit ordinal strictly greater than 0, is L of t b of alpha for alpha strictly less than lambda. I'm going to write it like that, same thing. Again, if lambda is strictly less than gamma. So basically an approximation satisfies the equations insofar as they make sense, given that the domain is the ordinal strictly less than gamma. And it's a trivial observation, so an easy observation. But if t from gamma to a is a gamma approximation, then t restricted to, I like to use this symbol for restricted to, the ordinal strictly below beta. So we simply, sorry, I'm going to write it like this, t restricted beta, to the ordinal strictly below beta. So that's a function from, the ordinal strictly below beta to a. That's a beta approximation for any beta strictly less than alpha, so than gamma. So when you've got a gamma approximation, initial segments of it remain approximations for the relevant ordinals. And then what we prove is the following statement, which I'll put down here. We prove for all gamma ordinal, for all ordinals gamma, there exists a unique gamma approximation we'll call it t gap, little t sub gamma, whose domain is the ordinals strictly less than gamma to a. And once we've proved the red box, once we have proved statement in the red box, to define T alpha to be T, the approximation little t at ordinal alpha plus 1 applied to alpha. So this obviously assigns us an element of the class A. And we need to know that it's going to satisfy these equations. Well, we get these equations from these equations. Only there's a little bit of a fiddle involved. I mean, it's not a fiddle, but there's something very slightly fiddly, which is each of these sets of equations is for a specific fixed gamma for the approximation. And here we're varying the index on the t. We're varying the domain of the t. But what saves us is this fact that together with that at every gamma there's a unique approximation. So that means when we look at the approximation for T gamma, I mean, if we look at any higher ordinal indexed approximation, we can restrict it back to T gamma. And because T gamma is, and it will still be an approximation because by this easy observation, and because of the uniqueness, it will agree. So basically, the uniqueness here tells us that all these functions agree with each other whenever they're defined on the same ordinal. And using that fact, these general equations easily follow from this. So the remaining thing to do is to prove this statement here. So how can we prove this? What method can we use? Transfinite induction, because once again, it's a statement of, so we've now reduced our theorem to proving a statement for that a particular statement holds for all ordinals. So we can apply that, we can approach that using transfinite induction. So in the notes, the case for gamma equals 0, we use the 0-step limit form of transfinite induction. The case for gamma equals 0 is 1 line. The case for the step case is 1 page and 2 lines. And the limit case is a page. Is 2/3 of the page. But in all the cases, essentially, well, I mean, the 0 case is trivial, so let's not consider this. The idea is the same for, I mean, the details are of course different for the step case and the limit case. So for the step case, you start off, so proving there exists a gamma approximation. So for the step case, we assume that we've got a gamma approximation for gamma, and we need to prove that we've got a gamma approximation for the successor of gamma. So for the gamma approximation for the successor of gamma, we need to define a function on all ordinals strictly less than the successor of gamma, which is the same as all ordinals strictly less than gamma union with gamma itself. So we can basically consider our approximating function T gamma defined on ordinals strictly less than gamma, and we want to extend that to deal with gamma itself. And so how we do that depends on whether gamma is a successor ordinal or it's a limit ordinal. In the case that it's a successor ordinal, we can simply apply f to the value we've already got for its predecessor. In the case it's a limit ordinal, we need to consider all the previous values and apply L to it. So we simply apply whichever one of these is relevant to get the next T, the T of the successor. Now there's something a bit funny in what I just said, because actually if we're going from no, it's correct. Yeah. And in the same way, in the limit case, we again sort of glue everything together. At least I think it's. The details are in the notes, and I think that's enough for today. So, are there any questions? Okay. Good. So today there are going to be 2 videos because I accidentally terminated the first one in the middle. The first one will be very echoey, but in any case, that's just how things worked out. So that's it for today. See you next week.